Hello everyone, I just want to walk you through a couple of the long answer question of this practice exam for Chem 10 for the first exam. And of course you will always be provided with standard information like the periodic table and very basic equations, but most of the equations you have to memorize. You also get a little bit of information of many questions you have. And by now you should have a copy of all the multiple choice problems. So here are some of the multiple choice problems. I'll just stay here for a second, but we discussed in detail how to solve every of these multiple choice problems in class. So you should have a good idea if something is like a buffer problem or weak acid pH problem, etc., and how to solve this. So here are the first 9 questions. Let's stay a little bit at the next questions, to question 16, 10 to 16. And there's even more questions here from 17 to 22. And of course the last questions till 25. Now when you watch the video you can stop at any time, pause it, and then just copy down the question and try to solve it, right? Technology, amazing. And when you're done you can double check your answer key. Now let's go and take a look at some of the more difficult long answer questions. Well, here's the first long answer question. It's basically an equilibrium between chloromethane and hydroxide in basic conditions. And in this reaction, you are given the equilibrium constant for this equilibrium, and you know it says equal volumes of 0.1 molar and 0.2 molar solution. So basically what you do is you are mixing a 0.1 molar chloromethane solution with a 0.2 molar NaOH solution. You have the equilibrium constant K, and you have the equilibrium expression, the equilibrium equation for this equilibrium. Now, in order to solve this, there's multiple ways to solve this problem. Okay, the first one is brute force. Well, brute force, you just write down your equilibrium, and for this equilibrium you just set up an ice table, right? And the reason why we want to set up an ice table is that the equilibrium concentration of OH minus is related to pH, and the problem is asking us to solve the pH when you mix a solution. So if I know how much hydroxide I have, I know what the pOH is, I know what the pH is, I'm done. Now if you do a brute force table, you need to know, hey, what are the initial concentrations? Well, there's a dilution effect. So this is 0.05 molar, this is 0.1 molar. Why? Because you mix equal volumes. Volumes means a 1 to 2 dilution, right? So this is a 1 to 2 dilution. Ah, great. So I have the initial concentrations, and of course my products are 0. Now if you think about it, then this should be minus x, plus x, plus x. And here are my equilibrium expressions for the concentration. Now if you want to solve this problem, then all you need to do is substitute these into the equilibrium expression, and the equilibrium expression is simply the concentration of Cl minus times the concentration of this guy, chlorhydroxide, over these two guys, right? Products over reactants. So basically what you do is you take your equilibrium expressions and substitute. Now when you do this, when you substitute these expression, there's a problem. And the problem is that you're gonna get more than quadratic powers in there. Okay, so that's kind of annoying to solve. Now, if that's annoying to solve and you don't really know what the analytical solution is and you can't make an approximation because k is not small, there's an alternative way. Okay, and this has been shown in your textbook, but I didn't show you in class. So it's an alternative way. And that is just to say, if k is 10 to the 16, right, which is very large, then the reaction goes to completion. Well, if it does, then the initial concentration is 0 for chloromethane and 0.05 for hydroxide, because all of the hydroxide and chloromethane react until there's no more chloromethane. And in the process, you produce 0.05 and 0.05. Okay? You might ask yourself, hey, how's this easier? Well, if this happens, then your change is plus x, minus x, and your equilibrium is x, 0.05 plus x, 0.05 minus x, 0.05 minus x. Now, again, this will be a problem where you just sub into k, and then you can solve a quadratic. Okay. Now, if you solve a quadratic in any way, you will find out that x is very, very tiny. It's approximately 0. Okay. Well, if that's the case, then the OH minus concentration is 0.05. The POH is minus log of OH minus concentration, and the pH is 14 minus POH, and in this case it's about 12.7. Okay, now in either case how you solve it, you can look at it and say, well, 10 to the 16, just, man, that thing goes to completion is all products. You can set up an ice table and do brute force and substitute stuff. You can also flip the equation, make your reactants your products and your products your reactants. Well, if you flip your equation, k becomes 1 over k, and then you can use the approximation. It doesn't matter how you do it, how you slice it. In the end, you all should get a pH of about 12.7. On to the next problem. In the next problem, we see it's a titration, okay? We see it's a weak acid, okay? And we see it's a strong base, okay? Now, in your brain, it should automatically say, hey, I've done so many of these problems. I've done this in lab, I've done this in my lab report or my formal report, I've done this in lecture, I've done this in homework, now I'm doing this in the practice exam. I asked you in lecture to memorize all the equations for all the different regions. So what do I expect? Well, first of all, I expect the pH curve to look something like this, where here you have the volume of NaOH added, and on the y-axis you have the pH. And the curve should look something like this, where we have the initial region, the buffering region, the equivalence point, and then the region after the equivalence point. So there's 4 regions, and we need to know what those 4 regions are, which equations fit to each region, and that you should have memorized. Well, let's take a look at region 1. So add 0 milliliters. Well, at 0 milliliters, we know it's just a weak acid in water. And how do we do this? Well, the weak acid, HA, forms H plus plus A minus, and you can do an ice table, or you should know that the H plus concentration is equal to the square root of Ka times your HA initial. Well, in this case, Ka is given, right? And that's 1 times 10 to the minus 4. And HA initial is given, which is 0.01 molar. And if you solve this, you get an H plus of 0.001. pH is minus log H plus concentration, and that's equal to 3. So here that pH should be 3. Okay, how about region 2? Add 25 milliliters of base added, right? We are in the buffer region. The pH is simply the pKa plus log moles of A minus divided by the moles of HA. And we know that the strong base, NaOH, completely converts the weak acid HA into weak base A minus. Okay, so in order to get the moles for this, you know that this one here is 0.025 liters times the concentration of NaOH, which is 0.01, right? The concentration of NaOH. And we know that this one here is 50, oh, let me step back, not 50, 0.050 liters times the volume of the acid times the molarity of the acid minus 0.025 times 0.01. And pKa obviously is 4. And if you do this, in the second region, pH should be equal to 4. So at 25 milliliters, the pH is 4. Okay. So far so good. We've done region 1, we've done region 2. Now at equivalence point 3, we first need to know what is the volume of equivalence point. So we need to calculate this. Well, you can do a basic stoichiometry calculation, or you can see in this case 0.1 molar, same molarity, requires same volume. So 50 milliliters of NaOH gives me equivalence point. Now, how do I calculate the pH there? Well, all of the HA is gone, right? All used up and converted into A minus. So really my equilibrium there is A minus, that's in water, and that forms back the weak acid plus OH minus, increasing the pH, making it slightly basic. Now, you can do an ice table, or you can memorize the equation where the hydroxide concentration is equal to the square root of Kb times A minus concentration. And now the A minus concentration depends on all the moles of HA that was converted into A minus, but it also depends on the 50 milliliters of base you added and the 50 milliliters of acid you have. So there's a total volume effect. So A minus here is equal to 0.05 liters times 0.01 molar for the initial acid, right, moles, divided by 0.1 liter, which is the sum of 250 milliliter solutions, right, the total volume. And if you plug this into here, and you know that Kb is Kw over Ka, right, then your POH is equal to 6.15, and your pH is 7.85. So we can see at equivalence point, the pH is slightly increased. Now, in region 4, it doesn't matter if we have a weak acid or a strong acid. Why? Because we added so much base that all the weak acid is gone. Now, how much did we add? 60 milliliters, right? And at 60 milliliters of base, there's an excess hydroxide. So what is the excess hydroxide? That is simply the 60 milliliters of base times the concentration of base minus the 50 milliliters of acid times the concentration of acid, and yes, you guessed it, divided by the total volume. 60 plus 50 is 110 milliliters. And if you do this, you get 9.09 times 10 to the minus 4 OH minus excess concentration, which gives you a pOH of 3.04 and a pH of 10.96. And here we have it, a weak acid with a strong base titration. Know how to calculate at each of the individual regions, 1, 2, 3, 4, what the pH is, memorize the equations, and also know how to get the volume of the equivalence point. Very important, because you need to know where that is on that curve. That is typically basic stoichiometry from the moles of acid you have. That has to equal the moles of base, and if you have the molarity of base, you can calculate how much volume you need. In this case, it was straightforward because it was 1 to 1. In this problem, we have a selective precipitation problem. And selective precipitation, there's two approaches to solve this, right? You either calculate what Q is and compare this to K, or you calculate what the anion concentration is and compare this to the actual, so you calculate what the anion concentration is to precipitate and compare this to the actual concentration in solution. So this is your thought process. Now you can solve it any way you want. You can calculate the concentration, you can calculate Q, and in the end you get the same answers. Now, what are all the possible equilibria you should look at for sure? Well, first of all, not this one here, because the K is larger than 1, that is probably not going to precipitate. The first one I would look at is this one here, 10 to the minus 39. Very negative, so I need to ask myself, hey, will this precipitate? The other one of interest are these two. So this would be my first one, this would be my second, this would be my third of interest that I would look at, okay, to see if things precipitate. Basic recipe, for each of those precipitates, write a KSP expression. Let's start with one. The KSP expression for this would be the concentration of iron 3 plus times the concentration of OH minus to the power 3. Okay, and that would also be the same expression for QSP, right? But using the initial concentration. Now, the question is, what is the concentration of Fe3 plus and what is the concentration of OH minus when mixing? We need to calculate this. Well, what is happening in this process here? Well, in this process, you have multiple solution mixed. When I read this, I already know, hey, there's some sort of dilution effect, okay? I also know that I have ionic compounds. So let's take a look at the iron concentration and the hydroxide concentration, okay? Where does the iron come from? Well, let me erase this real quick so we see the numbers better. Well, the iron, okay, that I want to calculate, this iron comes from this solution here. And then there's another solution mixed, which doesn't have iron, but changes the volume. So these are the two pieces of information. Well, first of all, I know that this guy here, for 1 molar of this guy, in solution, I get 2 molar of iron 3 plus ions. Okay, so there's a 2-to-1 ratio. So how do I calculate the concentration of iron 3 plus? Well, the concentration of iron 3 plus is equal to 1 times 10 to the minus 5 molar times this factor 2 over 1, because the iron sulfate solved in solution gives me 2 moles of ions, so there's a 2 over 1 factor, times the dilution factor. Well, I mixed 20 milliliters in a total of 100 milliliters. So my iron solution should be 4 times 10 to the minus 6 molar, if I don't worry about sig fixture right now. Okay. How do I get the hydroxide solution concentration initially when I mix? Well, barium hydroxide has the same molarity times 2 over 1. Why? Because every barium hydroxide gives me 2 hydroxides times 80 over 100 milliliters the factor, the units cancel out. And that gives me 1.6 times 10 to the minus 5 molar. Now, by definition, QSP is equal to the iron concentration when we mix times the hydroxide concentration to the power 2, and that gives me 1.638 times 10 to the minus 20 if I plug in all these numbers here, the hydroxide and the iron, into this expression. Since QSP is greater than KSP, you can show that hence there should be a precipitate of iron hydroxide. And I would expect it because that equilibrium constant is very, very small, but you should always check with calculation, right? Now, you can do for barium sulfate the second calculation, and you can calculate QSP the same way using the barium and the sulfate concentrations. You can do that at home, should be straightforward. You should get 4.8 times 10 to the minus 11. And since QSP is smaller than KSP, there's no precipitate. And you can do the same thing for barium hydroxide, and you should show that barium hydroxide will also not precipitate. So this guy here is the only precipitate you should see. Question 4 is a buffer problem, and more precisely how to make a buffer. And since tris is a base, you could remember the Henderson-Hasselbalch equation in terms of pOH, but I just stick with the acid kind of approach, where pH is pKa plus log of the moles of A minus divided by the moles of HA. And that could also be concentrations, but in this case, I prefer to use moles. Now, what is my HA? Well, my HA is basically tris plus an H plus. And my A minus is tris, and tris is this molecule here. And it makes sense because NH2 has a lone pair, it can accept an H plus from water. So this is a Bonsett-Lowry acid conjugate base pair, right? All right, now the question is, what gives rise to the A minus concentration? What gives rise to the HA concentration, or the moles, right? Well, let's look at the problem, okay? Now, if I look at the problem, I right away see there's 43 grams of tris, right? That should give me the moles of A minus if I know the molar mass. So let's do this calculation real quick. Moles of A minus is equal to basically the 43 grams of tris divided by 121.14 grams per mole, and that gives me 0.355 moles approximately of A minus. So we calculated the first component. Now, what happens to this buffer when I add the HCl, right? So I'm gonna add 0.095 molar HCl to make 1 liter, right? So basically what I do is, if I add 0.095 mole of HCl, now what happens is this will decrease the A minus amount by how much? Well, it will increase it by 0.095 moles, right? Because it's in 1 liter. And it will increase the HA amount by 0.095. Now, then really my A minus in this problem is 0.355 moles minus 0.095 moles, which gives me pretty much about 0.26 rounded moles of A minus. And this number here, which you can't read anymore, but this number here is this number here, 0.26 mole of A minus. The moles of HA, simply 0.095 moles, and then the pH is equal to the pKa. Well, the pKa, 14 minus pKb, is pKa. So that's simply 8.09 plus log of 0.26 divided by 0.095. And then if you just plug this in your calculator, you should get a number of about 8.53 SUPH. Okay? So this is how you do the buffer pump. Now, for this bonus question, you know there's 4 factors that we discussed in class. You might want to go back and look at the factors. Now, the first factor is atom. Atom, there's 2 effects, size and electronegativity. Size is the more important one, right? For example, HCl is a stronger acid than HF because Cl is bigger than F. And then for electronegativity, HF is a stronger acid than H2O, right? Because the size is the same. Same way on the periodic table, going from left to right, you become more electronegative in the periodic table, so that should be clear. Resonance. We discussed resonance in class. So if you have resonance, then you're more acidic. Induction. If you look at your lecture note, induction means, hey, you have to have an electronegative atom like oxygen, fluorine, chlorine, something like this, in the vicinity, which pulls on the electron density, makes it more stable. And we also talked about orbital and hybridization, and how a hybridized orbital can be more or less acidic depending on its S character, right? But review those from class. This was the bonus question. Bonus questions are always different, so don't expect this to be on your exam. Okay, I hope this helps. It's a quick solution key, and if you have more questions, come by in office hours or outside office hours.